Okay, thank you very much, Prof. Kamel. I am Ahmed Ammar. I am a doctor, a PhD from the University of Tunis Manar, Faculty of Science of Tunis. I will present you some activity in space weather in Tunisia, space weather activities. So space weather is the relation between the sun and the Earth. Space technology is exposed to space weather problems. So basically here GPS, communication, and human space exploration. So there is an international organization and space agency that are engaged in the research and the study of these problems. Many researchers all over the world are involved in this initiative. There is the International Space Weather Initiative. We are coordinator for Tunisia of this initiative. So many researchers are involved in this initiative, using ground instruments to study the Earth's ionosphere, magnetosphere. So many instruments are supplied to researchers. We have a VLF receiving station called Awesome. Donc, this station is installed at the roof of the Department of Physics at the Faculty of Science of Tunisia. Here, the map of the distribution of the station. There are two stations. The blue dots represent the Awesome station, which is dedicated for research. And the red dots for amateur, it's a network of SID instrument to study the solar flare impact to the ionosphere. This station are designed by Stanford University, and for Awesome station, which mainly for research. The team leader, the instrument leader of this instrument is Dr. Morris Cohen, which is a researcher at the Georgia Tech Institute of Technology. For the amateur instrument, which is super SID instruments, we have a very active group of amateur astronomers at the Astronomical Society of Tunisia. So they build antennas, and they have signal received from the station. This is, for example, a solar flare detected by our instrument in blue line. In red line, there is a detection from space GOES satellite. This is C5 solar flare. The instrument leader is Dr. Deborah Scherer from Stanford University. We have two stations, for one at the Faculty of Science of Tunisia and the other at the City of Science of Tunisia. So how to observe for example, we have two here receiver, VLF receiver, and VLF transmitter. So we receive the wave. If the ionosphere is disturbed, we can see that on our signals. For the disturbances, there is many factors. The solar activity, basically sunspot, solar flare, CME, For example, there are also we can detect the gamma ray burst, cosmic rays, and also perturbation from lithosphere, from earthquakes, for example. For transmitter, we have many transmitter we can observe. We can receive signals all over the world. Here a map of transmitter to our receiver in Tunis. And here a spectrum, broadband spectrum of frequency from 0 up to 50 kilohertz. So here the horizontal line represent artificial or made man station receiving signal, like here GQD from Britain and DHO from Germany. The vertical lines are signal from thunderstorm, so we can receive emission. Here, the observation of solar flare detected from Tunis. This is the impact to all over the continent, the African continent. It's an X1 X flare, solar flare. This is from the sun. And this is also the observation of ghost satellite compared to our VLF receiver. So we can see the similarity of the two observations. This is the directed from the sun, and this is the perturbation from the ionosphere. So this blue one, the blue signal, it's observed from Tunis. The signal emitted by NAA, 24 kilohertz transmitter. It's 6,000 kilometers distant from Tunis. Here also the American station received from Tunis. The red line shows the great circle path from Turkish transmitter, VLF transmitter. So we can see the to compare two signal, to receiving signal, the effect of day-night. There is a shifting between the two signal caused by terminator of sunrise and sunset. We can observe in the signal disturbances from solar flare. This one from this C solar flare, C-class solar flare. So we can see the disturbances in the two signal of two transmitter, the Turkish one and the American one. Also, we can see when we concatenate all the signals for 2 months, here from June to July 22. So we can see the effect of geomagnetic storm, body rate geomagnetic storm to the ionosphere. So we can see it to signals, to our receiver signals. And we do modeling and simulation using the LWPC code. We made open source free software developed by we developed in our lab. The super LWPC makes simple the use of the LWPC code, so we can find interactively with less error the parameter of the ionosphere after given disturbances. We made as input the observed signal, and we find the disturbance. We made it free and online. So GitHub, there is a GitHub link to our software. And why we use this as input, in general, as input is the signal, observed signal with the perturbation. We simulate this perturbation and to obtain the H' and beta, the two parameters described by the weight empirical model to inject in the formula of the electron density, which very important to telecommunication. If we find we can quantify the disturbances. So also there is another perturbation disturbances that we work. The disturbances caused by solar eclipse. Here a map of solar eclipse of 2015. So we did observe disturbances or on our receiving signals, and we made a model to quantify these disturbances. A new one that will be published soon. So to find the effect of solar eclipse